So here, let us discuss electron states and semiconductors. In the outset, free electron model, and this model helps us to understand very physical properties of metals. Okay, so according to this model, the valence electrons of the constituent atoms of a material. Okay, these are material and atoms are attached to lattice points, and the valence electrons of this material becomes conduction electrons. Valence electrons of this material becomes conduction electrons and can move freely through the material. Okay, through the volume of the material. It cannot go outside. It can move freely through this volume of the material. That means inside the material. Okay, so we used to introduce another term: free electron Fermi gas. Free electron Fermi gas. That means gas of electrons which obeys Pauli's exclusion principle. Okay. So consider a material having a volume and the valence electrons of the constituent atoms can move freely through this material. Okay, but it cannot go out of this material. It is restricted to move inside this volume of the material. Okay, so we need to reduce this into a one-dimensional problem. First of all, we can consider a one-dimensional situation. So, for one dimension, this is a length L, and this particle can move throughout this length, and it cannot go apart from this. It cannot go beyond this point. Okay, so that means in our term, in our language, in language of quantum mechanics, we can say that the potential here is infinity. If we are taking this as x-axis, the potential beyond the mode, if mode x greater than L, then potential is infinity. And here also the potential is infinity, and here the potential is equal to 0. Okay, so this problem is reduced into, or this problem is similar to the problem of infinity potential well. Okay, so the potential is 0, V is equal to 0. Inside this material, the potential is equal to 0, and outside this material, potential is infinity. So this particle cannot move out of this material. Okay, so first of all, we can consider one-dimensional case. In one-dimensional case, we are considering energy levels in one dimension. Okay, so electrons of mass n is confined to a length L by infinite barrier. This we are equating, or we are taking this as infinite, similar to infinite potential well. And the wave function psi n of x of the electron is a solution of the Schrodinger equation is psi equal to E psi. If a particle can move throughout this length and cannot go beyond this one, we can take the Schrodinger equation H psi equal to E psi, and in that Schrodinger equation, we know the Hamiltonian is minus h bar square over 2m d square psi n over dx square plus a potential energy term is there plus B is equal to En psi n. But here we are taking the potential is equal to 0 if mod x is less than or equal to L. Okay, so the potential is equal to 0. That means our Schrodinger equation becomes minus h bar square over 2m d square psi n over dx square equal to En psi n. Okay, the potential is equal to 0. And we know the solution also. We know the solution of this Schrodinger equation. We have derived in quantum mechanics. The solution is psi n is equal to a constant. I'm taking it as a constant sine n pi x over L, where L is the width of this potential well. Okay, so I got a solution. For a Schrodinger equation that consider an electron, and I got that solution here. Sine is equal to a sine n pi x over L, and we know the energy eigenvalues En is equal to n square pi square h bar square over 2ml square. I'm not deriving here. We have learned in quantum mechanics. So this two equations, sin n is equal to a sin n pi x over L, En equal to n square pi square h bar square over 2ml square. Okay. We use the term orbital to denote a solution of a Schrodinger equation for a system of only one electron. Okay, here we have solution sign is equal to A sin n pi x on L. This is the solution for a system of only one electron, and we used to represent it as, we used to denote it as orbital. Okay, if there are n electrons, n valence electrons, so n number of electrons, there are n solutions for Schrodinger equations, n solution for Schrodinger equation, and there are n orbitals. Okay, there are n orbitals. So we know the Pauli's exclusion principle. According to Pauli's exclusion principle, no two electrons can have all quantum numbers equal. There are two quantum numbers. Say n is principal quantum number and ms is spin quantum number. Okay, so there are pair of orbitals for electrons having spin up state and down state for same principal quantum number. Okay. If there are 6 electrons, that is n equal to 6, this 6 electrons can accommodate different orbitals. Okay, so electron occupancy, spin quantum number ms, and the principal quantum number n. Okay, according to Pauli's exclusion principle, no two electrons can have all the quantum numbers similar. Okay, so for one electron, it can accommodate n equal to 1 and spin up state. Okay, this electron can accommodate in this orbital, and for n equal to 1, spin down state is also there. That is considered as another orbital, and another electron can occupy in this, can accommodate in this orbital. Okay, so if n is equal to 2, there is up state, there is and down state. One electron each can accommodate in this orbitals. Here 3 plus 1 minus 1, and 2 electrons can accommodate in this orbitals. Okay, so for n equal to 1, there are 2 spin states plus up state and down state, and n equal to 2 as well as n equal to 3. For n equal to 3 also there is up state and down state. So these are considered as different orbitals. Okay, for n equal to 1 and n is equal to plus 1 is one orbital, n equal to 1 and minus 1 is another orbital. In that manner, we can accommodate all 6 electrons in this orbitals. Okay, and if we are taking NF as the topmost filled energy level, here NF is equal to 3, and we know number n equal to 6. So the relation between the topmost filled energy level and number of electrons is NF equal to n over 2. Okay, NF equal to n over 2, or we can write 2 NF equal to n. Okay. Now let's define the Fermi energy. Fermi energy is EF, used to denote EF. The energy of the topmost filled energy level in the ground state of n electron system. When we are considering a ground state of n electron system, this is the Fermi energy, is the energy of the topmost filled energy level. Okay, so we know energy eigenvalues is equal to n square pi square h bar square over 2 ml square. Okay, and NF is the topmost filled energy level. So the Fermi energy is the energy of the topmost filled energy level. EF is equal to NF square pi square h bar square over 2 ml square, and we know NF is total number divided by 2. So this is n is the number of electrons, n over 2 whole square pi square h bar square over 2 ml square, and this can be written as h bar square over 2m into n pi over 2l whole square. Okay, this is the Fermi energy. Okay. Here, let us discuss Fermi-Dirac distribution function. Okay, for that, we can define the ground state. The ground state is the state of any electron system at absolute zero temperature. Okay, when we are considering a material, having a volume V, and this has many atoms, constituent atoms, and that atoms have electrons, free electrons that can move freely through the volume of the metal. Okay, and at absolute zero temperature, the ground state is defined as the state of any electron system at absolute zero temperature. That is known as ground state. If we draw the energy levels, this is n equal to 1, this is n equal to 2, this is n equal to 3, 4, 5, etc. Okay, if we take n is equal to 6, for n equal to 1 level accommodated by 2 electrons with opposite spins at absolute zero temperature. Okay, and here this also accommodated, this also occupied by 2 electrons, and this also occupied by 2 electrons with opposite spins by obeying Pauli's exclusion principle. At absolute zero temperature, this is the energy level diagrams, diagrams, and Fermi-Dirac distribution function gives the pattern of shifting of the particle when temperature increases. Okay, this is at absolute zero temperature. When temperature increases, this electrons will get excited and this will go higher energy levels. And our Fermi-Dirac distribution function gives how this electrons shifting to higher energy levels, the pattern of shifting of electrons from lower energy levels to higher energy levels when temperature increases. Okay, and Fermi-Dirac distribution gives the probability that an orbital at energy E will be occupied in an ideal electron gas in thermal equilibrium. That means if we are considering an energy level here, Fermi-Dirac distribution function gives the probability of occupation of electron at this energy level. We usually represent Fermi-Dirac distribution function like this, f of E. That means the probability, this gives the probability of occupation of electron at the energy level E. This will get from value 0 to 1. Okay. So the Fermi-Dirac distribution function is defined like this: f of E is equal to 1 over e raised to E minus mu over kt plus 1. Okay, where mu is the chemical potential, and case the Boltzmann constant is the temperature. And chemical potential mu is defined as this is equal to Fermi energy EF at absolute zero temperature. Okay, so chemical potential is defined as the Fermi energy at absolute zero temperature. This is the energy of the topmost filled energy level. Okay, so f of E equal to 1 over e raised to E minus mu over kt plus 1. We defined the Fermi-Dirac distribution function like this, and we need to consider two cases. Case 1, at absolute zero temperature, we are considering these cases. Case 1 is if E is less than EF. That means we usually draw the energy level diagrams of this electron system. N equal to 1, this is n equal to 2, this is n equal to 3, 4, n equal to 4, etc. Okay, so if we consider total number of electrons is equal to 6, then we can draw like this. Two electrons are in this state, then another two with opposite spins like this. Okay, and this energy levels are vacant at absolute zero temperature. Okay, this is n equal to 4, n equal to 5, etc. So this is n equal to 3 is the topmost filled energy level. So here NF is equal to 3, and here I can denote EF. Energy of this level is EF. Okay, energy of the topmost filled energy level is the Fermi energy, and when E less than EF means we are considering these levels. Okay, we are considering these levels. If E greater than EF, we are considering the levels above this energy levels. Okay, above this Fermi energy level. Okay, so for at absolute zero temperature, if E less than EF, then the probability of occupation of electron in that level is equal to 1 over e raised to E minus at absolute zero temperature, mu is EF. So E minus EF over at absolute zero temperature we are considering, so this is equal to 0. Plus 1 is equal to 1 over E raised to, if E less than EF, this is minus infinity plus 1 is equal to E raised to minus infinity is 0. So 1 by 1 is equal to 1. That means we got the probability is equal to 1. Probability is 100% at absolute zero temperature. If we are considering energy less than EF, energy less than Fermi energy level, we are getting this is F of E is equal to 1. That means that levels must occupied with electrons. Okay, and we need to consider another case, case 2, that is E is greater than EF. At absolute zero temperature we are considering. In case 2, E greater than EF, so the probability of occupation of that energy level with electron F of E is equal to 1 over E raised to E minus EF over 0 plus 1. Okay, here E is greater than EF, so we get 1 over E raised to infinity plus 1. E raised to infinity is infinity, so 1 over infinity is equal to 0. That means the probability of occupation of electron above this Fermi energy level. Okay, if E greater than EF means this energy levels. Okay, this energy levels, the probability of occupation of electron in that energy levels is equal to 0. So there will not be any electron occupied in this energy levels at absolute zero temperature. So if we draw a graph of Fermi-Dirac function versus energy level, versus energy, we get a heaviside step function like this. This is EF, energy level EF, and the probability is maximum when energy is less than EF, and minimum or 0 if energy is greater than EF. Okay.